Sometimes people think that just because we're using like something on the calculator and it's kind of actually works and it's nice, that somehow it's just for fun. But this is like a skill that you want to have. This is part of calculus that just actually uses some technology. The other thing is people will start to quickly say, well, how do I use this? Or what kind of problem am I going to do? So I'm going to show you. And then you guys are actually going to do an exit ticket that that also kind of takes you through exactly what you need to do. If you look at number 25 on page 312, a couple things you should kind of say, even though we've only seen one of these. You should say, oh, that's a differential equation. dy dx equals 1 over 1 plus x squared. Now, if we just stop right there, that is what gets turned into a slope field. This is important. You got to realize that dy dx is a derivative equation. So what I'm trying to show here is there's nothing that you have to do yet, except understand that this is the equation that goes into the slope field. So I type in 1 over 1 plus x squared. Remember, you put that in the y equals screen. That's like a storage spot. Do you realize why I'm making a little bit of a mathematical deal out of this? You're typing in dy dx, but you're typing it as y equals. It seems like it's a little bit of a conflict of interest. But that's the way the program works. Okay, and unless you want to change the window, and sometimes people are like, well, how do I know if I want to change the window? You'd have to explore, but I'm going to keep it a Zoom standard. I'm going to choose slope field in the program and run that program. Not every slope field is like built the same. Okay, here we have a slope field that's not real fancy. It always reminds me of that game Frogger. Can someone give me some love? Do you ever play Frogger? Okay, thank you. There's basically a frog that's trying to get across the logs or the cars. I guess they've come up with different names for it, but originally it was Frogger. Anyway, now what? Well, it says that y of 0 equals pi over 2. Y of 0 equals pi over 2. That just means when x equals 0, y equals pi over 2. It basically just means there's a point. And it's probably right around here. And where's my pen? Whether you want to write on your calculator, which you're not going to do, but you basically can take that point and kind of see a line that probably goes with the flow. Now, what I just did right there would be something that you more do just kind of mentally. You kind of see that there's this flow to the slope, the little slope segments. So how do we answer the question? I want you to understand that simply you're just matching that to graph A, B, or C. Actually, I didn't realize that's all it was. Yeah, you're just graphing it. You're just matching it to A, B, or C. So yeah, I forgot that was already down there in your book. Obviously, it's not graph A and it's not graph C, so I guess it would have to be B. Here's a little extra. Just to be clear, we answered the question. It's B. But here's a little extra, because this is what you're going to do on an exit ticket. There is kind of like an algebra side to this. To put it another way, it's the antiderivative. Uh-oh. You mean I'm supposed to know the antiderivative of 1 over 1 plus x squared?
Inverse tangent.
Yes, thank you. Inverse tangent. Inverse tangent. Now, do you understand what's going on here? We didn't really need to do this to answer this question. 2 minutes ago, we said graph B. But it doesn't hurt to make a connection. Maybe you already know what's going to happen. But inverse tangent is the solution. And so is that graph that we chose, graph B. So, as I hope you're realizing, they're the same thing. I only get one chance to do this. Oh, I should have technically done the pi over 2 thing. I should have solved for C. Now, I did some of that mentally, but if you solve for C, C equals pi over 2. That makes my graph match a little better. again, you basically look at this and you say, yes, you say it's like what it was supposed to do. Let me take you through one more, although I really hope that you say, well, it kind of seems like what we've done now a few times, but this is kind of what you do. You find the antiderivative, and in the languages, you support it with a slope field. You find the antiderivative, and you support it with a slope field. This is what you're going to do on your exit ticket. I thought we would model it for you just one more time. Also want you to come to the realization that it kind of doesn't matter what you do first or second. Like the problem that we just finished in the textbook, we kind of did it visually first. This problem we're going to do more algebraically first. So it doesn't so much matter which one comes first. It just you want to understand how they support each other. Okay, so I have this nice little dy dx. It's called a differential equation. I actually made one that's supposed to be easy, that you're not overthinking it. You're just going to find the solution. I hope you add to the exponent. Now you divide by the new exponent, so that's obviously just going to be x cubed. And then that 2 right there, make sure you understand that 2 becomes 2x. Now there's always a plus c. I have to confess I forgot it on this inverse tangent over here, but we'll put plus c on this guy and certainly plug in 0 and 1. Careful, don't falsely come to the conclusion that that c always equals this point. This point is just used to help you get c. Obviously, since this is a basic polynomial, c equals 1. But it's not always the case. You basically want to solve it. Okay, but our solution is x cubed plus 2x plus 1. X cubed plus 2x plus 1. And I would think that most of us, all of us, say, yeah, I know that that's right. Good, good. Support it. Support it with a slope field. And so just one more time. And I'm telling you, when you guys do some of these on your own, this is usually the main question. You know, what do I type in? Okay, you type in the differential equation. You type in dy dx. It's like a storage spot. So I also wanted you just to see another slope field, because again, they are not all built the same. This one almost seems like the reverse of the other one. So how in the world do you go with the flow? What's the graph look like? You want to interpret this as being very steep slopes. So most likely we have a graph that's going to be very steep. And you don't have to draw that graph. You really don't have to draw it. Maybe you kind of can see it, but it's supporting it. It's supporting it when I type in x cubed plus 2x plus 1. This is the part that you do have to do. And you get one chance to do it right. And it looks good. What's up with the rest of those lines? Well, that would be as x goes out to negative 10 or 10, which is going to be some gigantic y value. It's just, we don't see it on the graph. This would have been a good example of changing the window to maybe make it look a little nicer, but what I'm showing you here is good enough. Now, people sometimes say, how do I do this on an assignment? Well, you'll find on the assignment that I give you some directions, and essentially it says to draw 4 lines. I think I say 4 lines of a slope field. So I erased that one from the beginning of the period, but you saw me draw about 4. I probably could have drew about 4 lines of this one and been satisfactory. On the exit ticket, though, you guys are going to show me your calculator. You're going to show me your calculator, and I'm going to initial it to kind of say, hey, you got the idea. So you don't have to draw anything for the exit ticket.
Thank you.
But you do have to show me your calculator.